Hi, I am Mats Oberg, Associate VP for DSP Architecture at Marvell Semiconductor. Today I'm going to talk about computational storage, or SSDs that think. Please feel free to add questions to the chat button on the right side of your screen. The overall concept of computational storage is rather simple. Compute where the data is. With offline computation and storage, we can make some sense of unstructured data and thereby increase its value. Our focus in this presentation is on computational storage for offline computation. Computing where the data is has a benefit that it avoids major data movements, and this will increase the overall efficiency in terms of power, performance, and cost. And this can be done by adding compute engines for data processing to the storage devices. People have been mining forever. In the 1800s, we were rushing for gold. In the 1900s, they focused on the black gold, also known as oil. Data is the mine of the 21st century, and information is the gold. And there is plenty of data to mine. It is estimated that by 2025, 175 zettabytes of data will be generated, with a compound annual growth rate of 26%. Although only a fraction of this data is expected to be stored, it's still expected that 80 to 90% of all stored data is unstructured, also known as dark data. And this is an enormous opportunity for the data analytics market that is growing at over 13% per year, expected to be worth over 500 billion in 2028. So what is unstructured data? What is dark data? Well, it is unrefined data that requires more work to make it usable. Structured data is already refined data where the data's purpose is already determined. As an engineer, I view dark data as unstructured data is not analyzed. We see some examples in the figure to the right, for example, log files, employee data, financial data, old files and notes, and so on. Unless we know what the data is and have some structure, it is difficult to use. So how can we get value out of dark data? How can I analyze the data and put some structure to it? And here we have computational storage to the rescue. As I mentioned before, moving data around is expensive. We view it from the edge point of view. We need to consider upload throughput to the core, latency for the data to be moved to the core for computation and then back, and of course the power of all this data movement. In the cloud, we have overall efficiency concerns in moving data around, heterogeneity of data and equipment, and of course, network bottlenecks. So consider this traditional CPU-centric architecture. You have a whole CPU with memory connected to external storage through a NIC, a bunch of local drives. The PCI bandwidth to the drives is high, and it's just getting higher with each generation. But with centralized computation, all data have to move to the host CPU and DRAM. So there are several bottlenecks for this. For example, DRAM throughput, massive data movement, and compute capabilities fixed, even as the storage capacity keeps growing. So we add more drives, we don't increase the compute capability. With computational storage architecture, we can add, and here I go to the SNIA definition, 3 types of computational storage. Computational storage drives, CSDs, which is basically an SSD or HDD with its own computation capability. CSP is a computational storage processor. It does not have its own storage capability and sits alongside other drives. And a computational storage array is a collection of drives, CSDs or regular drives, or computational storage processors. This allows computation to happen where the data is, and we can parallelize compute, use host CPU and DRAM for what it's really needed, which can optimize throughput and capacity. With reduced data movement, power and latency is reduced, and as you add more storage capacity, the system scales. You get more compute capacity as well. So how do we add value with the help of computational storage? As I mentioned, we view the primary value of computational storage to be in offline work. that is optimal way to do non-latency sensitive computation. This can be analyzing and trying to make sense out of dark data, structure or pre-process data for later processing by the host, and compute and draw conclusions from the data inside storage. I'll go a little deeper into each one of these three items in the next few slides. Analyze the data, basically figure out what the data is, for example, type of data, object sentiments present in the data, and so on. Transform the data into knowledge by tagging it with metadata in the form of a high-level representation of the data. For example, we can tag images as shown in the figure to the right, for example, containing animals, landscapes, or transportation. We can, of course, add additional tags for cars, trains, trucks, buses, public transportation, freight, morning, evening, lion, zebra, and so on. So we can add additional labels as the host needs, basically anything that adds value for the host to the data. And by doing this inside the storage device, we limit data movement, minimize the host CPU resource usage, and we can parallelize it over enormous sets of dark data. And all this can be done offline. So if we now look at structure, it's basically, we have some basic structure to the data, so we know what it is. But now we can pre-process the data inside a storage device prior to providing it to the host. For example, if the host is running a deep neural network and they want to operate on images of a certain size, then the computational storage device can decode and resize the JPEG images prior to sending them back to the host, basically prepare them for the neural network. If you have a database that want to utilize machine learning, then it may be helpful to scale and normalize data, and in some cases encode words into numbers for easier computation by a neural network. It's a little hard to make mathematical operation on a word, so it may be better that we give them numbers. Another use case for computational storage is to filter and select only relevant data to send back to the host. For example, the host may ask the storage device to find images of cars and send them back to the host, or only send back database records related to France. There's multiple opportunities. So in this case, we use computational storage device to support the host by offloading part of the computation. If we now look at the next one, we do full processing inside the drive itself. This, of course, comes in many flavors too. If we, for example, assume a new algorithm has been developed for autonomous vehicles to better detect, let's say, stop signs in rain. Of course, a neural network has been trained and validated on a large number of images and video feeds that has been uploaded to the cloud. But this is still only a small fraction of the data that's generated by millions of cars on the road. So before the algorithm is fully deployed, it could be sent to vehicles for offline validation on data stored inside computational storage devices in potential millions of cars. And a new algorithm can then be compared to the existing algorithm and fully validated that, yes, this is robust. As an example is offline video transcoding. A streaming service that needs to transcode large number of stored movies can initialize offline transcoding inside computational storage devices. And another example we consider is reprocessing of medical images with, for example, a new algorithm to detect a certain form of cancer. So a new algorithm has been devised. We want to check it on kind of old images, and we send it out to the storage devices to do the processing. So these are kind of the three ways we kind of view how we can do computational storage. So let's look at a little example on kind of big data analytics, kind of trying to summarize this. Okay, so assume we have a drive that contains the data. It is not clear what the data is or how it's related to other data. For example, the data on the drive is really what we call dark data. So what is it about? In this example, we then say, well, let's utilize a neural network depicted on the lower left-hand corner. And we send images. So we'd read images from the NAND and send them to the neural network inferencing engine. And the neural network inferencing engine creates data labels based on the data and sends it back to the kind of storage in the form of tags or metadata, and store this along with the data. And all this is possible with a computational storage drive that incorporates this neural network inferencing engine. And this helps the user understand the content of the data, relationship, and possibly the importance of the data. A different view of how offline or background AI inferencing can be done inside storage. Basically, load a trained neural network AI model to the AI engine, and we can pass images stored on the device through to the neural network and provide labels for each image. Showing here, kind of, we have something that looks like a bird, goes through the network, and maybe it's detected as a bird. And of course, this AI model needs to be selected to generate the metadata based on what the host is interested in. So maybe the first step is to, as we did before, with landscape, animals, transportation, and then we have an even finer network that goes in and classifies them as what kind of animals there is. So why do we really want to do this inside the storage? Coming back to this. Well, consider if we do this metadata tagging at the host, we would need to read the data from the NAND and return it to the requester over the network. And this type of remote processing results in large amount of data traffic, and the host CPU will be kept busy, either moving the data around and sending to accelerators. So if we instead were to utilize, do this inside the storage devices, we would need to move the data over the network, and the network traffic could be significantly reduced. And moreover, we can utilize the host CPU and accelerators for higher value computation. And as mentioned before, as we add more storage, the compute capability scales with it. So summarize with some key takeaways here. We can improve value of dark data with the help of computational storage. Tag data such that it makes sense for the host. And we emphasize the offline processing part at the storage device. This can be to analyze and tag the data, make some sense of what is this data. Pre-process data to streamline host processing. So mentioned, for example, a neural network may want to have data normalized before it receives it, or images resized. And kind of last one we mentioned was do full processing of the data at the device. Just return the result of the computation. Ubiquitous AI inferencing drives many opportunities for computational storage. Thanks for your attention, and please take a minute to rate this presentation. Thank you.